Alright, we're in chapter 9 now, and the title of chapter 9, obviously written here, is Calculations from Chemical Equations. What chapter 9 really is it's a combination of the quantification of chemical compounds that we learned from chapter 7. Remember, we talked about the mole as the central unit of chemistry, and we talked how to convert quantities of substances in and out of the mole using different conversion factors. And then in chapter 8, we talked about chemical equations that were used to describe chemical changes. And we learned about balancing chemical equations, and that the balanced chemical equations, the coefficient written in front of the balanced chemical equation, that number was the number of moles in the quote-unquote recipe, if that's what you want to think of a chemical equation as. So in chapter 9, what we're doing is we're combining the two. We're going to look at chemical equations, quantities of reagents stoichiometrically given as mole ratios, and we're going to do calculations involving those mole ratios of reactants to products. So we're going to be converting things in and out of the mole from one reagent to the other. So let's go back to chapter 7 real quick, and let's just remember a few things we described. The first thing we talked about in chapter 7 was the mole. The mole is the central unit of chemistry, and a mole is 6.022 times 10 to the 23rd of anything. That number, 6.022 times 10 to the 23rd, remember that's a special number called Avogadro's number. So it could be a mole of molecules, a mole of formula units. If you have an ionic compound, like a formula unit for sodium chloride would be 1 sodium chloride unit. A mole of atoms, a mole of ions. So Avogadro's number relates to a mole, and we can come up with a conversion factor that 1 mole of anything is Avogadro's number, 6.022 times 10 to the 23rd of anything, right? 1 mole of anything is Avogadro's number of anything. And when we write that as a ratio, it's a conversion factor. And we can either put the mole on top or we can put the mole on bottom. Alright, so the mole is the central unit for counting. We also talked about the molar mass. Remember talking about the molar mass of compounds? The molar mass units are always grams per mole. And what molar mass was, I guess I wrote it right there, is it's the sum of all the atomic masses of all the atoms in a compound, or if you're just an element, it's just the mass of the atom, for 1 mole. So how much does 1 mole of atoms weigh, or how much does 1 mole of the compound weigh? So it's grams per mole. Remember that we had to calculate the molar mass. So before we get started, and you're following along in this lecture, I will say that in chemistry class, when you're watching a lecture, you always need to be an active learner, right? So I want you to practice all of these problems too. So hopefully you've got a periodic table out, because we'll be using that a lot. And we will also need your calculator. So I've got my calculator right here beside me. I know you can't see it. And I've got a periodic table too. So let's practice just reviewing how to calculate the molar mass. That's the mass per 1 mole of compound. And this compound is aluminum chlorate, AlClO3, 3. All right, I'll write that again in case you can't see it. AlClO3, 3. Aluminum chlorate, an ionic compound. So here's how we solve this problem. Remember that we first want to add up all of the molar masses of all the individual elements, and we have aluminum, chlorine, and oxygen in our compound. And we want to multiply the number of each type of ion or atom with its mass. So how many aluminums are there? There's only 1 aluminum in the compound, and each aluminum atom, the molar mass found in the periodic table for aluminum, is 26.98. What are the units? Grams per mole. Remember, for every measurement, there's always a number and a unit. Alright, for chlorine, how many chlorines are there in aluminum chlorate? There are 3. And chlorine weighs 35.45 grams per mole. Okay, and then we've got oxygen. How many oxygens are there in aluminum chlorate? There's 3 in the chlorates, but we've got 3 chlorates, so 3 times 3 is 9. And oxygen's molar mass is 16 grams per mole. Alright, so what we're doing here is we're coming up with the total weight of aluminum, the total weight of chlorine, and the total weight of oxygen. And when we get all of those totals, we're going to sum it all up. So I'm going to pause this, I'm going to get out my calculator, I'm going to do this. And you see if we get the same answers. Okay, I came up with 26.98 grams per mole for aluminum. I came up with 106.35 grams per mole for chlorine. And 144.0 grams per mole for oxygen. Actually, that should technically be 106.4 if you think about significant figures, but it'll all round anyway. So my answer then that I end up getting is 250.4 grams per mole. That was the sum of all of the aluminum, chlorine, and oxygen. That's the molar mass of aluminum chlorate. Alright, so we'll keep that molar mass here because we're actually going to use that in the next part of the problem. The next problem says calculate the number of formula units. That's the, for aluminum perchlorate, 1 aluminum, 3 chlorines, and 9 oxygens makes up the formula unit of aluminum perchlorate. So calculate the number, we're going to be using off of Gaudreau's number, it seems like, of formula units contained in 12.4 grams of aluminum chlorate. So notice we're given grams, and this is a review, so you probably remember this from Chapter 7. If not, go back and watch Chapter 7 again. Make sure you know how to do these conversion factors. But here we're given grams, or the mass, and we're going to start with what we're given. We're given 12.4 grams of aluminum perchlorate. We need to find the number of formula units. Can we go from grams straight to numbers of something? No, remember the central unit in chemistry is the mole. So any conversion we have to do, we always have to go through the mole unit. So I need to convert grams first to moles of aluminum chlorate. Whenever I have grams per mole, that's our molar mass. We just calculated that from above. We know there are 250.4 grams for every 1 mole of aluminum chlorate. So I had a grams on top, a grams on bottom, they cancel. Now I can convert from moles of my aluminum chlorate, got a mole on top, a mole on bottom. I can convert to formula units of aluminum chlorate. And there's, for every mole of anything, there's how much? 6.022 times 10 to the 23rd of anything. So here I've got formula units. Alright, that's my little abbreviation for formula units. Alright, so now we're just going to solve. So we've got 12.4. Put that in my calculator. 12.4 divided by 250.4 equals times parentheses 6.022 times 10 to the 23rd. I get, and let's see, we've got 3 significant figures here, so I'm going to have 3 significant figures in my answer. I get 2.98 times 10 to the 22nd formula units. Does that number make sense? Well, if you have 12.4 grams of anything, that's a lot. That's definitely an amount you can see. And remember how small ions and elements and compounds are. They're very, very small. So it makes sense that you're going to have a lot of them. So that's our answer. Okay, so that's a review of what we did. We did conversions in and out of the mole in Chapter 7. Let's talk about stoichiometry now. Alright, so this is a big word we actually saw in Chapter 7 when we were talking about energy and energy changes in chemical reactions. We talked about exothermic and endothermic reactions. And we said that when heat was gained or lost from a chemical equation, it was lost stoichiometrically. What does that mean? What is stoichiometry? Stoichiometry deals with the quantitative relationship, so the amounts, between reactants and products in a balanced chemical equation. And the example I'm going to use is this reaction shown here below. Now, obviously, we don't write ones as coefficients in balanced chemical equations, but you'll see why I did it in this one instance. It's a no-no, you don't do it. But the reason I did it here was to show you the stoichiometry of the balanced equation. If we look at this equation, it reads that 1 nitrogen molecule plus 3 iodine molecules will yield 2 sodium iodide molecules. Now, I just read that chemical equation on the molecular level. But remember that I can also read chemical equations on the mole scale. And that's the quantitatively large scale that we typically manipulate chemicals in. So stuff you would weigh out in the lab. So let me read that again. I could also read that as 1 mole of nitrogen molecules plus 3 moles of iodine molecules yields 2 moles of nitrogen triiodide. All right. The numbers in front I read as the number of moles. Those numbers in front, remember, are called the coefficients. So the mole ratio comes from the coefficients there we go. The coefficients in the balanced equation. Now, what's a mole ratio? Well, if I was going to run this reaction, and I said, well, I want to make 2 moles of 2 moles of nitrogen iodide, triiodide. I've got 3 moles of iodine. How many moles of nitrogen do I need? So if I know that I want to make 2 moles of product, and maybe I look and I say, I've got 3 moles of iodine, how many moles of nitrogen do I need? Well, all I have to do is look at the balanced chemical equation. In the chemical equation, the coefficients that are written in are the mole ratios of reactants to products. It's the balance formula in order to produce the right amount of products without any leftovers or anything that's you don't have enough material. It's kind of like reading a recipe. When you read a recipe, there's a certain amount of each part or reactant that you need, each ingredient, I should say, in order to make the finished dish. So when you make a cake, for instance, you need 1 whole box of cake mix, if you do it that way. You need 3 eggs, you need 1/3 cup of oil, and you need 1 cup of water. That's the balanced list of ingredients. If you go in and you add 2 cups of water to 1 box of baking mix, you're going to have a really runny, not tasting good cake, because the stoichiometry, or the quantitative relationship between the ingredients to make the correct product, is already in place. That's what these mole ratios are. Turns out we can use the mole ratios to solve problems, and we'll get to that in a second, but let's just look at the mole ratio now. Mole ratios are actually our 3rd conversion factor in this chapter. In the chapters we've looked at so far in this unit. We've got Avogadro's number, which relates the numbers of anything to moles, and we know what Avogadro's number is. We've got molar mass, which relates the gram quantity, the mass of anything, to the mole of that reagent. And now we're going to have mole ratios. Sometimes books call them mole-to-mole ratios, because that's exactly what they are. They tell you the moles of the one reactant to another reactant or product in a balanced chemical equation. So here's some examples. In this balanced chemical equation, for every 3 moles of iodine that I have, I need also 1 mole of nitrogen. That's what this equation shows. Now remember that just because you write a conversion factor or ratio in one way does not mean that you can't write it in the other way. I could have also written this conversion factor as 1 mole of nitrogen over 3 moles of iodine. It's the same relationship, moles of nitrogen to moles of iodine. I've just inverted it. Another example, I could relate the moles of iodine, my reactant, to the moles of nitrogen triiodide, my product. In the balanced chemical formula, there's 3 moles of iodine for every 2 moles of nitrogen triiodide. That's what this mole ratio is showing here. For every 3 moles of iodine, there are 2 moles of nitrogen triiodide. Once again, we could reverse it. We could put the nitrogen triiodide on top, the iodine on bottom. But I think you get the point here. These are mole-to-mole ratios. Now, why in the world would we need mole-to-mole ratios? We're going to use them to solve problems. Let me just erase this. If I'm given the amount of one reagent, let's say that I'm given moles of nitrogen, okay, X moles of nitrogen, and I know I have so many moles of nitrogen that is given to me. Let's say I want to know how many moles of product I can make from that many moles of nitrogen. So I want to know how many moles of nitrogen triiodide I can make. Do you notice here what we have is we're given moles, our quantity is moles of one reagent, and we're asked to calculate a quantity of a different reagent. This is the first time we've ever seen a problem like this. Every time we've done conversions in this unit, we've always converted from the quantity of one reagent to a different quantity of the same reagent. Here we're given quantity of one reagent, but we're asked to find the quantity of a different reagent. The only way that you can convert quantity of one reagent to a different reagent is to go through the mole ratio. You need the balanced chemical formula to solve this problem. If you're given moles of nitrogen, you're going to have to write moles of nitrogen in the denominator in order to cancel out not just that quantity, but also that compound. And you're going to have to convert to moles of the new compound. So here we want to convert from nitrogen to nitrogen triiodide. So my mole to mole ratio will have nitrogen in the bottom, one on top, one on bottom, and it will have my new compound that I want to convert to on top. The numbers that go in front are the coefficients of the balanced chemical equation. On the bottom, for every 1 mole of nitrogen, 1 mole of nitrogen, we need, how much will we produce? We will produce 2 moles of our compound. So this is what a mole to mole ratio is used for. It's used for converting quantities of one reagent into quantities of another reagent, going through the mole unit. The only way you can convert from one reagent to another is to use the mole ratio. So it's very important. Okay, so let's practice, because this is the best way to learn how to use a mole ratio. So just do some problems. So let's practice using mole ratios to convert from one reagent quantity to another. So let's look at the first one. It says calculate the number of moles of nitrogen triiodide that can be made from 5.5 moles of nitrogen in the following reaction. Now, once again, we're given a balanced chemical equation. It's the one we just looked at, actually. Now, do we usually write 1 in the balanced chemical equation? No. Usually you don't write 1, it's understood. But for this problem, since we're just starting, I'm going to write it there as a reminder. But I'm going to drop it off as we go. So you won't see the 1 there anymore. Okay, let's read the problem again because I completely forgot what I was doing now. Alright, it says calculate the number of moles of nitrogen triiodide. So that's our unknown. We want to calculate that. How many of that can be made from 5.5? Oh, there's a number. That's our given quantity. Moles of nitrogen in the reaction given. Okay, so first of all, we're going to write down what we're given and what we need to find. And when it comes to stoichiometry problems, I'll tell you a few hints. First of all, how do you know you have a stoichiometry problem from Chapter 9 versus Chapter 7? There's one really easy way to know. If you have a Chapter 9 problem, you not only have a word problem for conversions, you are always given a balanced chemical equation. We weren't given those in Chapter 7. We were only given the word problems for conversions. For every conversion in Chapter 9, you have to have a balanced equation to get started. So when you see both of those combined, the first thought you're going to say is, oh, word problem plus equation. This is a stoichiometry problem, Chapter 9. I'm going to need a mole to mole ratio. That'll be the crux of the problem. Okay, so that's my first word of advice. The second word of advice is you always need to figure out what you're given and what you need to find, and I use the balanced chemical equation as kind of my solution map, what I'm going to do. So here we're given 5.5 moles of nitrogen. I'm going to come over here to where my nitrogen is. See my nitrogen? 1 nitrogen? I'm going to write down underneath it how much I'm given. I'm given 5.5 moles of nitrogen. And now it's asked me to find how many moles nitrogen triiodide that would make. So how many moles, that's the question mark, moles of nitrogen triiodide. All right. When you calculate of the quantity of one given reagent to the quantity of the next chemical reagent, what do we always go through? What's the unit? It's always the mole. Notice I'm given the first unit in moles, and the unit I have to convert to is moles. So what ratio will I need? I'm going to need a mole-to-mole ratio to solve this problem. All right, so I'm going to set it up. I'm going to start with what I'm given. I'm given 5.50 moles of nitrogen. And notice I'm writing the nitrogen down. That's because I'm going to be converting to moles, but to moles of a new substance. So I'm going to keep track of what substance I have. All right, notice I want to convert from moles of nitrogen to moles of nitrogen triiodide. So I've got a mole of nitrogen on top. I'm going to put my moles of nitrogen on bottom. This is the best way to do stoichiometry or conversions. Just put your units that you need to cancel first. And now I'm going to put the unit I need on top. I want to convert that to moles of nitrogen triiodide. All right. Now what numbers am I going to have? For molar mass and for Avogadro's number, we always related every other number to 1 mole. This will be the first time that we can actually have multiple numbers in front of moles. The numbers come, once again, remember, from the balanced chemical equation. So here, for every 1 mole of nitrogen, we make 2 moles of nitrogen triiodide. So now we've set our problem up. We've converted 2 moles of nitrogen triiodide, so that will be our unit. And we've got 5.50 times 2. That's 11.0 with 3 significant figures. So that's our answer there. Now, you probably came up with this a long time ago. You probably said, well, if 1 mole of nitrogen makes 2 moles of nitrogen triiodide, I'm just going to multiply 5.5 times 2. And you probably got this answer a lot faster than me. I bet I would too. I don't know if I would always use this method if I could see the answer clearly. But what we're going to find is this is a very easy question. The questions we're going to go to are going to be more and more complex, and you won't be able to do them in your head. So we're starting with easy questions so that we can set them up on paper and learn how to work them. All right, let's do the next one. It's going to use actually the same equation, so I'm going to erase this equation here. The next question says, calculate the number of moles of iodine that will react with 5.5 moles of nitrogen in that chemical reaction above. So now our given, once again, is 5.5 moles of nitrogen, but our unknown is moles of nitrogen. So we're going to start with what we're given. We're given 5.50 moles of nitrogen. And we want to get rid of the moles of nitrogen. We're in the moles, so we can just do a mole-to-mole conversion. And now we want to convert that to number of moles of iodine. So we have a mole-to-mole ratio, mole on top, mole on bottom. The reason I put the moles of nitrogen on bottom is they cancel, right? So where are we going to find the conversion vectors, numbers for our mole-to-mole ratio? Back in the equation. So here, for every 1 mole of nitrogen, how many moles of iodine do we need? We need 3. So now our mole-to-mole ratio is 3 to 1. So we have 5.5 times 3. Well, that's 15.5. And our units are going to be moles of iodine. So we need 15.5 moles of iodine for every 5.50 moles of nitrogen that react. That's the answer. Not too bad, right? Let's look at a different one. The last one here says, how many moles of HF? So here we have a new equation. Hydrogen plus fluorine yields 2 hydrofluoric acid. It says, how many moles of HF, so that's what we're going to solve for, are produced by the complete reaction of 1.42 moles of hydrogen in the following equation. All right, I'm going to go to the next page here. I'm going to rewrite it for you. We've got hydrogen plus fluorine yields 2 hydrofluoric acids. Okay, that's a balanced equation. By the way, if it's ever not balanced, make sure it's balanced before you start your stoichiometry problems. Okay, we were given 1.42 moles of hydrogen. So over here by hydrogen, I'm going to write my 1.42 moles. And we were asked to find how many moles of HF that would produce. Now, if we look at the balanced chemical equation, we're going from, by the way, moles of hydrogen to moles of HF. When you're converting one reagent quantity to another reagent, you always have to use what ratio? The mole ratio. Okay, so you always have to go and use the mole ratio. So let's start with what we're given. We're given 1.42 moles of what? Of hydrogen. And we're going to convert that to moles of HF. So I've got my moles of hydrogen on bottom because I'm going to cancel out the moles of hydrogen and convert on top moles of HF. Alright, so what's my mole to mole ratio? Notice here we have a regular balanced equation. There's no number written, but we assume that means there's 1 mole of hydrogen. So for every 1 mole of hydrogen gas, we produce 2 moles of HF. Alright, so we're going to multiply it, right? 1.42 times 2 is 2.84 moles of HF. So we're going to produce twice as much HF in moles. Alright, so that's how you use mole to mole ratios. Okay. In the next video, we're going to use mole to mole ratios and do more complicated stoichiometry problems.